Worth it. My name is Dries Cronje, and I design deep learning systems. And a vital part of deep learning systems is to get the big data and cloud integration in place. I will be using this platform today to show you that it is possible to leverage the power of big data and to use cloud integration technology into your physical world to enhance your reality, to augment your reality. The system is aware of its own surroundings by using a combination of computer vision system, IoT, and a smart assistant to interact with the system. If we take the long Wikipedia definition of augmented reality and we reduce it to the most basic idea, augmented reality is an advanced version of reality. To demonstrate my ideas on augmented reality, I built a system that incorporates a computer vision system, IoT, and a smart assistant. I'm going to take you through each of the parts making up the system, and only at the end will I reveal my, and only at the end will I reveal my secret. I've prepared a diagram to set out the major steps we need to take in order to complete the system. First, the first step is IoT. An IoT device is used for reading sensor values and sending it to the cloud and to control specific aspects of our environment. The second step is that of computer vision. The computer vision system is used for real-time object detection and to identify individual objects to target specific objects in the environment. The third step is that of the smart assistant. The smart assistant is used to interact with your environment. And the final step is to put it all together. IoT, the Internet of Things. When you search the web for IoT, you quickly get an idea of what IoT is all about. The common theme pulling through is that of lots of nodes near the edge, and they're all connected to the cloud. High-level speaking, that is exactly what IoT is all about. Devices connected to the internet. In 1999, Bill Gates used the analogy digital nervous system in describing the then modern enterprise. Today, IoT gives that modern enterprise system a finger on the pulse. It gives it sensors. If you take my system as an example, chili plants need a lot of sunshine and regular water to grow. And so it would be extremely useful to use an IoT device to read light and soil moisture levels from sensors and send those values to the cloud. And use the same IoT device to control parts of the system. For example, switching a plant growing light on or off. The IoT device I use for my project is the particle photon. The particle photon can send data collected from the sensors to the cloud, and it can receive messages and react on those messages coming from the cloud. The photon is powerful, it's dead simple to connect to the internet, and it comes with an awesome maker community. When you decide on going the route of IoT, do not underestimate the importance of the supporting backing systems. Most IoT projects fail because companies fail to anticipate how hard it is to set up these supporting systems. The particle photon system ticks all the boxes required for an ecosystem to support your project. There's the particle cloud that takes care of the cloud backend. There's the fully featured web IDE. Firmware updates are done over Wi-Fi, and the maker community. If we look at the diagram of the particle photon, we are interested in the analog pins on the left-hand side for analog measurement readings, and the digital pins on the right-hand side is used to switch devices on or off. To measure light and moisture levels, I used a photo sensor and a soil moisture sensor kit from a local electronics shop. If we look at the soil moisture sensor, by measuring the resistance between the probes, you can calculate the level of moisture in the soil. The light sensor works in a similar way. Here we can see part of my system where I connected the soil moisture sensor to a particle photon to measure moisture levels in the soil. The goal is to stream measurements into the cloud and save the measurements into BigQuery to feed the rest of the project with data. I used the Particle Cloud webhook to stream data to PubSub. From PubSub, I used the data flow to stream data into BigQuery. We will look at each of these steps in more detail. To send the data from the sensor to the Particle Cloud, I wrote a program on the particle photon and read measurements from the sensors and sent those values to the Particle Cloud. To write the program for the photon, I used the Web IDE. A photon program consists of two main parts, the setup and the loop. The setup is where you do all your initializations and set up your variables, and in the loop, it's where you do your readings. You do your measurement readings, and you send those to the cloud. To send measurements to the cloud, I used the built-in library, and I published the values to a specific topic. Take note of the topic. You will need to subscribe to this topic a little bit later. Now that my device is sending values to the Particle Cloud, I configure a webhook to be triggered when the new values are published to a specific topic, and those values are then sent to PubSub. A webhook is an HTTP callback to any RESTful service that is connected to the internet. PubSub is a highly available Google Cloud messaging service, and in most cases, this is your entry point into the Google Cloud. To allow communication to travel freely between the webhook on the particle side and PubSub on the Google Cloud side, you have to use a Google Cloud integration. There are two main things that needs to be done when setting up an integration. You create a topic. This is important because your webhook will relay messages to this topic. And secondly, as you will see now in this small animation, you need to set up a particle user to be a member of the Particle Cloud, to be a member of the Google Cloud, and give that user enough rights, read-write rights. Everything is set, and we should now be able to stream data from the particle photon to the Google Cloud. Here we can see a very SQL-like query I've done on BigQuery, and data that's through from my actual soil measuring sensors into BigQuery. The first important step is done. We are streaming measurements to the cloud. Now we move on to computer vision. The ability of deep learning to find patterns in unstructured data makes it ideal for computer vision tasks, and has already surpassed human level accuracy in many tasks that were once thought only humans were capable of. If we take a convolutional neural network as a popular implementation of a deep neural network, and we look at the layered approach to get a better understanding of how deep learning neural networks work, the first layer of a convolutional neural network extracts low-level features, and each layer builds on the previous, extracting more high-level features than the previous. Taking a face recognition model as an example, we see the low-level details as those of being lines, shadows, and contrast. And from the second layer, we can now make out larger objects, those being a nose, an ear, or a mouth. And by the third layer, we can actually make out faces. It's important to note that these aren't actual faces, but rather the learned representation of what the model thinks a face looks like. Being able to classify an image was the first step in the evolution of the modern computer vision system with deep learning at its core. For the computer vision system to be used in an augmented reality system, the object detection needs to happen fast, in real time, on a video feed. And the path from image classification to blazing fast real-time object detection was one of natural progression. First, we classified an image, that is everything in the window. Then we progressed to be able to locate an object and draw a box around it. And then we classify and locate multiple objects in an image. To achieve object detection, the obvious way was to systematically slide a window of various sizes across the input image and perform classification on the image under the window. The problem with this approach is the insane amount of processing power needed. A lot of research has been done on using different techniques to statistically find regions with a high probability of being an object, and to only do classification on those regions. Although a big improvement, still too much processing power is needed for practical purposes. It turns out that you don't need to slide a window across your image. You can package the whole image as a single input of multiple regions and send it through the network. The network will predict bounding boxes and probabilities for each region, all in one pass. By iterating through each bounding box, looking for categories with a high probability, objects of interest are quickly recognized and located. The technique is fittingly called YOLO. You only look once. YOLO is the current state of the art, and I will be using YOLO for object detection in the rest of the system. I've used a TensorFlow implementation of YOLO trained on COCO. COCO is a popular data set to train localization models on common objects. YOLO is really efficient and leaves plenty of room for more processing power to be done. I've seen YOLO run on a Raspberry Pi. Let's look at a code snippet of the main loop controlling the object detection. In an infinite loop, I continuously read a frame from the camera. The image is packed as a 3D array to be compatible with the input tensor. And we use 3 tensors to evaluate the input tensor. There's one for boxes, scores, and classes. Boxes gives you your bounding boxes of the detected classes. And classes and scores are the predicted classes and the confidence that it is the object that you predicted. My implementation of YOLO in action on some common objects in my man cave. Don't know where that teddy bear came from. Now that we can find objects, and we even know what class they are, there's one important missing step. Visual object identification. Not only do I want to know that these are 2 plants, I want to know which plants. I want to identify them. I want to know their names. Let's call them Charlie and Rufus. By knowing the identity of each plant, I can get more contextual information about the plant, such as soil moisture readings, which I've already sent to the cloud. Okay, before I get carried away, let's get back to the object identification. You will see later why it's important to identify objects. A good example of visual object identification is the facial recognition capabilities of Google Photos. From thousands of photographs, Google can identify your family, your friends, and now even your pets. This is all great when dealing with individual objects with different visual characteristics, but as one of my mountain bike buddies pointed out, not very useful in a factory where all the machinery looks the same. I had to come up with a different approach, a simple, practical way to identify objects. I want to show you that if the basics of deep learning are well understood, it is not that hard to come up with novel ideas to use deep learning in a practical and in different scenarios. I based my idea on the interesting idea of using stickers to fool neural networks. I thought that if you can fool a neural network into thinking a photo of a banana is that of a toaster by showing it a sticker, why not use that same principle to use stickers to identify objects? Here you can see my stickers for Charlie and Rufus, hand-drawn and completely random. I used a VGG-like convolutional neural network to train the stickers on. Each layer consists of convolutions, activations, and pooling. To train the system, I generated plus minus 3,000 images using a webcam from all sorts of angles and different light conditions. To make sure the model differentiated between the stickers and not the background features, I mixed up the backgrounds. Looking at a code snippet, I used the same TensorFlow session I previously used for the yellow object detection, and I swapped my identification graph model into that same session. Each time I found an object that is of the class I'm looking for. I present to you Charlie and Rufus. And to make sure you believe me that we are actually identifying objects and not objects based on the stickers and not on features in the background, I swapped the stickers around. Rufus and Charlie. We are taking measurements from the environment, and we are now able to identify objects in the environment. The next step is to use the smart assistant to interact with our environment. For example, to be able to ask Charlie, what is your soil measure? What is your soil measurement? I will use the Google Home Assistant to interact with Charlie and Rufus. Smart home devices let you turn your home into an automated, voice-activated, and app-controlled hub. Key to the usefulness of the Amazon Echo or the Google Home Assistant is their ability to leverage the power of IoT. How useful a smart assistant is to you is very personal. And in the same way, my mother always said, do not get into arguments about religion or politics. This is an argument I won't get myself into. No, I'm more interested in the speech recognition capabilities of the smart assistants, the ability to recognize spoken language and convert it into text. A case in point, the ability to recognize English accurately with my rather strong Afrikaans accent is something my smart home assistant is doing better than my wife. I hope you have all been able to follow me so far. Okay, good. The task of speech recognition is to map an acoustic signal containing a spoken natural language utterance into the corresponding sequence of words intended by the speaker. To understand how speech recognition works, I will break speech recognition down into a few basic building blocks. An intent represents a mapping between what a user says and what action should be taken by your software. An entity is a mapping of synonyms to a reference value. We want to know what objects the user is referring to. An action is a step your program will take in response to a specific intent being triggered. And context. Context is helpful for differentiating phrases which may be vague or have different meanings depending on the user's preferences, geographic location, or the topic of conversation. We will use the Google Home Assistant and Dialogflow framework for speech recognition. Here we can see how I used Dialogflow to train an intent to switch a light on or off. Notice the three different entities extracted from the intent. Extracting entities as parameters helped me to target specific devices in my environment. I built a small Flask web service webhook to handle actions triggered by the Google Home Assistant. Dialogflow has clear requirements which are well documented with regard to handling incoming requests and responding response messages. The service is hosted as a microservice on the Google Cloud. Hosting the webhook as a service is very handy and makes it simple to send messages to the particle cloud to target specific devices or retrieve historic values from BigQuery, and to relay those messages back to the Google Home Assistant. I have now shown you how to use IoT to collect measurements to gain a better understanding of your environment. I've also shown you how to use computer vision to detect and identify objects in your environment. I've also shown you how to use a smart assistant to interact with your environment. Most of these are state-of-the-art technologies. Even though it might come across as if I'm a Google salesman, I have built the system to be like Lego blocks. Each block could be swapped out with a different technology. For example, the Google Home Assistant can be swapped out for Alexa or Slack integration. Please join me now and watch a short video I have made showing the action with all the building blocks put together.
Give me the moisture reading for Rufus.
The moisture value for Rufus is 83.
Turn light for Rufus on.
Sure.
Give me the moisture reading for Rufus.
The moisture value for Rufus is 83.
Turn light for Rufus on.
Sure.
Turn light for Charlie on.
Sure.
What is the moisture reading for Rufus?
The moisture value for Rufus is 83.
Turn light for Rufus off.
Sure.
Turn light for Charlie off.
Sure.
Thank you for your time. I have thoroughly enjoyed presenting to you today. Using technology to build systems that has the potential to impact the lives of the people around us is my passion. I challenge you to think of applications for the system and the ideas that I have presented to you today, and come to me afterwards and let's have a conversation and see how we can put your ideas into action. If there are questions, I'm happy to take them now.
My question is,